Now let's come to the distributed system lecture 2 that we know that distributed systems also require a rigid theory to support them. And for example, we have the series of distributed computing, the distributed counterpart of the theory of the centralized computation of the sequential algorithm. It's like the distributed counterpart of the theory of centralized distributing of the sequential algorithm. So it's like distributed computing. Because why do we care theory that much? Because the theory can provide insight into the existing system, which can allow to argue about any potential system. For example, to prove that what is in principle feasible in a given setting, or prove what is impossible for a given setting, which means that we need to prove that whether it's possible or not. And the formal method that is going to be the follow model is going to be distributed as follows. We have processors, and they have a network of directed graph of G, V, E, with the number of nodes within this network is going to be the number of vertices within this network. And we have different examples like the ring, tree, and complete network. And the distributed algorithm may assume a specific topology or not. Maybe some kind of distributed algorithm may only work with maybe the complete network rather than tree or ring. And let's see the number of edges, just like this is the edges, this is the edges, this is the vertices, this is the vertices, this is and for this ring topology, which means that every node may have exactly 2 neighbors, and for this tree topology, maybe more neighbors or possibly. And what is this one? What is this a system bus or something? I'm not sure. Okay, so this one is not that sure. Okay, this is it another edge? I think so. So how do we display the maybe topology for tree topology? And for a complete network, we have each node may have n minus 1 neighbors. Therefore, let's continue on the displaying what are the processes within the network. So process U displaying consists of 3 sub. What is the relationship between the status messages and with the processes? Okay, that's not intuitive. Let's see the status U, which means the set of status. We have the initial state start U, and the holding state halt U, and all the subset of states. And the message is U, which means the status U Cartesian product with the outer neighbors of U, which is going to be generated the set of M union with null. And the trans U means the status of U, Cartesian product with the messages of all the of the messages generated by the incoming neighbors to the power of the number of incoming neighbors. We're going to be generated a set of states U. So this is called a state transaction function, and this is called a message generation function. Let me look at them in detail. That firstly, the state means that each state is going to denote the whole status of the all the nodes in the network, and the message is going to be the status as long from each status. If you have the outgoing neighbors, then you can generate the corresponding messages or none of the messages. For example, let's say you and your mother is a distributed network, and you have your status maybe 0 or 1, maybe you are awakened or not awakened, and you have now neighbors, maybe your mother. So the status U, let's assume that if you are 1 and your mother is 1, you are going to call your mother. So that which means that you will the status U, which means you and you and both you and your mother are both 1, and then you are going to call your mother. So that is you are going to call the out neighbors, which is your mother. I'm not sure whether the out neighbors outside the distributed network, right? It's outside the distributed network. How about communication within the distributed network? It's going to be yeah. So in general, that the message as you means all the possible status, the status of you times the nodes that from these states that can reach out, and it's going to generate a combination of it's going to be generating a set. It's going to be generating a set of the messages. So this is a set of the messages. And the trans U means the status U times the messages of the set of the messages from the generated and to the power of number of incoming neighbors, which means that every messages that we received from one node, we are going to change our status to a new status, and we have that number of incoming neighbors, so we are going to times this to the power of that. This is the C transaction function. So let's talk about the synchronous network and the asynchronous network. So in every cases, we are going to talk about the synchronous network in this module, and which means that all the processes are in the initial state, and all processes repeat synchronously in a lockstep. So the lockstep means that it's like a waterfall method, which means that the first one must stop before the second one starts. And we are going to apply the message generation function, and the message is produced. Firstly, we generate the message. We have defined our initial state, then we can generate the message. And the message is maybe produced to the output neighbors. And then the message is transmitted through the corresponding channels. And then we apply the state transaction function into account to many received, which means that I think this one can be assumed to be the emitter, and this one can be seen as the receiver, which means that from the receiver side you apply the C transaction function and to remove all the messages from the channel. So based on the step 1, step 2, we have one round. The illustration I followed, where we have the status, which is A, B, and C, which is a generalization for the status, this one, this node, and this node, this 5 nodes. It's a generalization for the status within all these nodes. And the messages, which means maybe wake up, this is wake up, this is like go to bed, and maybe also no. And what if a node is in status 1, and it will give his first neighbor the message on 1. And what if the node receive a message? It's in status A, and it will give his second neighborhood a value of no. And what if a node that is in status A, it will give his third neighborhood the message 3. And we define a transaction function, which means that if a node is in status A and it have received the message 1 from the first neighborhood, message 2 from the second neighborhood, and no from the third neighborhood, and M2 from the last neighborhood, the fourth neighborhood, we are going to transmit from the state A to state B. So the illustration are as follows. So what if the states are at A? So let's say this is at A, and we we are going to generate the message 1 to his first neighborhood, message 2 from his node to to the second neighborhood, and message 2 from the third neighborhood. And then another how do we interpret the trans function? Transaction function means that we are going to, if we from the M1 from the first neighborhood, M2 from the second neighborhood, M0 from the third neighborhood, and M2 from the fourth neighborhood, we are going to transmit this A to B. Then, and we would like to define the flooding example, which means that initially the inner node has a token, and the goal is that all the nodes must learn the token. And so the idea is that, for example, like on wireless sensor network, where the node detects the fire, and all nodes must be informed about the location and to act accordingly. So initially, the leader node has a token, and all nodes must learn this token. So the idea is that all nodes are initially awakened, and if the nodes learn the token, that as long as the token go to that state, that is fine. And if the beginning of this round you are awake and you have a token, forward to your neighbor and sleep. If you are asleep, do nothing. And then this is the